When you hear the word infinity, what do you imagine?
2,
Do you picture a line that never ends,
4,
time continuing forever,
6,
or maybe the
7,
universe?
8,
Personally, I think about space. Not because we know that the universe is infinite, we don't. The observable universe is roughly 92 billion light years across, but science still cannot tell us the total size of everything beyond what we can observe, or whether the entire universe is finite or infinite. Today, I want to talk about something that seems very simpler: numbers. Because unlike the universe, numbers seem to reveal their infinity almost immediately. I remember that when I was in elementary school, my math teacher would ask us to write numerical sequences, by 2s, by 10s, or by the 50s. Sometimes we continued until we filled an entire page, or more. And strangely, I loved doing it. There was something incredibly calming about watching the pattern continue. When I got home, I would make the sequences much larger. Instead of counting by 2s or 10s, I would count by thousands, or sometimes by 500,000. But eventually, I realized something. The page could end. My pencil could run out. I could get tired. But the sequence itself would never have to stop. No matter how far I counted, there would always be another number waiting. And that made me wonder, what is the largest number? 1 million is a 1 followed by 6 zeros. 1 billion is a 1 followed by 9 zeros. And 1 trillion is a 1 followed by 12 zeros. Those definitions are simple, but they don't communicate how enormous the jumps really are. So let's measure them in seconds. 1 million seconds is approximately 11.5 days. 1 billion seconds is almost 32 years. But 1 trillion seconds is more than 31,000 years. A trillion has become familiar through economics. In 2026, estimates of Elon Musk's net worth briefly crossed $1 trillion, leading to headlines calling him the first trillionaire. A trillion also appears inside us. The human brain contains approximately 86 billion neurons. But the number of connections between those neurons, the synapses, is commonly estimated at around 100 trillion. In other words, the complexity of the brain doesn't come only from how many cells it contains, but from the enormous network those cells create. Research reviews support estimates of approximately 86 billion neurons and around 1 times 10 to the 14th power synapses. But now, let's keep climbing. A quadrillion is 1 followed by 15 zeros. Here is one way to find that number. A light year, the distance light travels in 1 year, is approximately 9.46 quadrillion meters. That means even when astronomers say that something is only 1 light year away, they are describing a distance of nearly 10 quadrillion meters. Next comes the quintillion, 1 followed by 18 zeros. Researchers have estimated that the observable universe may contain around 40 quintillion stellar mass black holes. 1 followed by 24 zeros. Take an ordinary 250 milliliter glass of water. It contains approximately 8.36 times 10 to the 24th power water molecules. That is more than 8 septillion molecules inside something you can hold with one hand. The calculation follows from water's molecular mass and the exact Avogadro constant of 6.02214076 times 10 to the 23rd power particles per mole. And here's the beautiful comparison. Astronomers estimate that the observable universe may contain up to roughly 1 septillion stars. So a single glass of water may contain several times more molecules than there are stars in the observable universe. NASA gives an upper estimate of about 1 septillion stars. Of course, molecules and stars are completely different things, but comparisons like this help our minds approach quantities that would otherwise remain meaningless strings of zeros. Eventually, we reach the decillion, followed by 33 zeros. The mass of the Sun is approximately 1,989 times 10 to the 33rd power grams. So, expressed in grams, the Sun weighs almost 2 decillion grams. Interestingly, if we express that same mass in kilograms, it almost becomes 2 nonillion kilograms. The sun didn't change, only the unit did. That reminds us that the names we give enormous quantities depend on what we are measuring and how we choose to measure it. Now let's make an enormous jump. The observable universe is estimated to contain approximately 10 to the 80 atoms. That is a 1 followed by around 80 zeros. It is not an exact count, of course. We cannot visit the entire observable universe and count every atom individually. It is an order of magnitude estimate, derived from the amount of ordinary matter cosmological models indicate should exist. But imagine that every atom in the observable universe could represent one number, one digit, or one physical mark. Eventually, the universe would run out of atoms. Mathematics still wouldn't run out of numbers. The Googol. A Googol is 1 times 10 to the power of 100, 1 followed by 100 zeros. The name was reportedly created in 1938 by Milton Serrata, the 9-year-old nephew of mathematician Edward Kasner. Wolfram MathWorld gives its history and complete decimal expansion. A Googol is already vastly greater than the estimated number of atoms in the observable universe. But unlike some of the numbers we are about to discuss, a Googol can still be written in full on a piece of paper. It is enormous as a quantity, but not enormous as a written expression. And this distinction is essential. The size of a number is not the same as the length of the notation used to represent it. The Googolplex. A Googolplex is a 1 followed by a Googol zeros. Now we have crossed a physical boundary. You could not write a Googolplex in full, even if every atom in the observable universe somehow became a tiny piece of ink representing one digit. There simply would not be enough atoms. Yet I just represented the entire number using a very short expression. The number is not impossible to represent. It is impossible to expand physically into all of its individual digits. And mathematics is extraordinarily powerful because a small collection of symbols can describe something larger than anything the physical universe could display. Graham's number. But even a Googolplex is tiny compared with Graham's number. To understand why, think about how mathematical operations compress repetition. Multiplication is repeated addition. Exponentiation is repeated multiplication. Then we can build power towers, repeated exponentiation. And after power towers, mathematicians can define operations that repeat the process again and again at entirely new levels. Graham's number was created as an upper bound connected to a problem in Ramsey theory, a branch of mathematics concerned with patterns that must eventually appear inside sufficiently large structures. The complete definition uses a notation called Knuth's up arrow notation and builds through 64 recursive stages. Even its first stage is so enormous that talking about trillions, decillions, or Googolplexes no longer helps us understand it. Graham's number is finite. At the time it became famous, it was described as the largest number used in a serious mathematical proof, but that never meant it was the largest possible number. The American Mathematical Society discusses Graham's number's historical role. Beyond Graham's number, mathematicians have defined numbers that make Graham's number appear almost insignificant. One example is tree, a finite number arising from a problem involving sequences of labeled mathematical trees. Then there is Rayo's number. It was introduced by Mexican philosopher Agustin Rayo during a 2007 large number duel at MIT. Instead of constructing the number through ordinary arithmetic, its definition refers to all numbers that can be described using fewer than a Googol symbols in a particular formal language, and then defines a number larger than all of them. That single definition takes us beyond Graham's number and tree. But even Rayo's number is not the largest number, because we can still add 1. So what is infinity? This brings us back to our original question. Infinity is not simply an extraordinarily large counting number. It is not waiting somewhere after Graham's number or Rayo's number. In ordinary mathematics, infinity describes something without a finite boundary or endpoint. Every number we have discussed, even the ones whose digits could never be written using the entire universe, is still finite. Infinity is different, and it becomes stranger. Mathematics contains different kinds and even different sizes of infinity. When I was a child, filling those pages with numerical sequences, I thought I was simply completing a math exercise. But without realizing it, I had encountered something much deeper. The page had an ending, the sequence didn't. And perhaps that is what fascinates me most about numbers. With only a few symbols, the human mind can describe quantities larger than the universe could ever physically contain. How can a finite mind understand, or at least define, something that no physical universe could ever write down? What do you picture? Space? Time? Numbers? Or something else entirely?